Okay.
JP Rihanna or something. What's his name? He's married to someone. Jacobian.
So
Let's go back.
just remember the next Wednesday is the exam. This is new stuff, so this will be on the final, but not on the exam of next week. So for the final. The final. Um, Usually this is like the last section of chapter 15. So we still need to discuss triple integrals. It's just that on this section has two parts on the book. If you're checking the book, one is for double integrals and the other is for triple integrals. So we're going to do only in the course we only do the double integrals version. So that's why it kind of makes more sense to cover this now, because that way we keep talking about double integrals. So on Monday we'll start talking about triple integrals. So today is kind of like the last thing about double integrals that I'll mention. And this also fits nicely with the stuff we were talking about polar coordinates. So it's like a nice like ending to that topic. So um, let me start by just like giving you like an example of what we want to discuss. So So let's say that you have, like maybe you're trying to do like a double integral and the region of integration is going to be the unit disk. So let's put here, x squared plus y squared equals, um, well, let's see, should I put one or, yeah, that's fine. That will be fine. So let's say you want to like do like a double integral over the unit square. Well, now we know that kind of the best idea is to use polar coordinates. There is another way to think about this region of integration, which is closer to what we're going to do today, and that it consists in like kind of introducing a new set of axes. Okay, so usually like here, like our coordinates or our axes are x and y, but now I'm going to kind of draw like a diagram or a plane where one axis is like the angle theta from polar and the other axis is the angle is a variable r from polar coordinates. So if you want, let's call this xy plane because the variable like the axes are labeled x and y. And I'll now talk about a different plane, which I'll call like the theta r plane. By that, I just mean like, for example, like I'll take the like the horizontal line to be theta and the vertical line to be r. Like there's not much of a, like obvious choice of as to which should be the horizontal one and which one the vertical. So it's a little bit like up, like, arbitrary which one you take to be like, to be horizontal. Okay. Um, so this is like, similar, like there are like things of that sort that you do all the time in other places. So like, for example, in physics, so we'll see like all these diagrams of like time against like, position against time. So you just introduce like time as a like horizontal variable. Or like if you take like chemistry, you'll do like this like PV diagrams, like where you have pressure and volume, right? So it's very common to, just put like axes which are different from like puts like the spatial axis, that you see like with your like literally with your eyes. So if you do, what's the kind of like consequence of doing that? Um, so what happens if you do this is that remember that the unit circle in polar coordinates was r squared equals 1, right? Or r equals 1, right? So if you are trying to draw the unit circle in this plane, right? You are trying to draw the equation r equals 1, but drawing r equals 1 is because this is playing like the role of y. Drawing r equals 1 is the same as drawing y equals 1. So this actually corresponds to a line on this plane, if that makes sense. So this is kind of like the line r equals 1. And if you remember, for the theta in polar, like if you're on the unit disk or the unit circle, like the theta will go from 0 to 2 pi. So you put here, if you put here 0 and 2 pi, right? What that tells you is that the unit disk, right? Like this was like the unit disk, the way we typically see it, but like on this diagram or on this plane, if you prefer, the unit disk becomes like a rectangle of sorts, right? So like this is what would correspond to the unit disk in quotes, right? So that's how it would look like on this diagram. Is that making sense? So by changing the coordinates that you're using to make the picture, by using different axes, like the effect is to distort like the image, right? So you like in this perspective, like the regular disk, what you would call the disk, with respect, it's almost like like a camera filter, like on the phone, like it just distorts like the image and it turns it into a rectangle. Okay. And now what you know, so what happens here? So what happens when you distort the image? So that has the effect that you cannot compute the area in like, for example, a naive way. So for example, we know that like the area of what is the area of the unit disk, right? So the area is pi r squared, right? This is like a circle or a disk of radius 1, so it's just pi in this case, right? So we know that that's kind of like the right answer for the area, but if you just like try to find the area from this picture, right, you would say, well, this is a rectangle, right? And what's the area of a rectangle? The area, I'll put it in quotes because you'll see that it's wrong, right? So the area would be like base times height, right? So it would be 2 pi times 1, which would be 2 pi, right? Um, so what that means is that, if you just try to, for example, find the area naively, right? You cannot just do it from the picture because like it will come with the wrong answer, and it kind of makes sense because if you imagine like, if you think about what's going on, you're literally distorting the image. So like there's no reason why the area should be preserved. But that is one of the reasons why when you have like a function, like when you were integrating like a function like times dy dx, here on the regular plane, when you switch it to polar, right? Like you had to put like the r the theta, right? Because in a sense, this r factor is when we think about it from this perspective, it's kind of like a correction or like something that keeps track of the distortion of the space that you made. So that's why, like, when you do like a double integral in polar, you can't put just like the r d theta because that would be like doing treating this like as if it had like the correct area of a rectangle. So this, you should think about it as some sort of like this correction factor for like the distortion that was created, when you switch like your perspective on the picture. So I think, this is some sort of like correction factor. To account for the distortion in the shape of the region. Is that making sense? So what happens when you make a change of variables, like for example, from Cartesian to polar, is that if you were to draw the picture, like with respect to the new variables, like yeah, the figure gets deformed, and that's why when you have the double integral, you cannot just like have like something like dr d theta. You have to put an additional term. So this happens more generally, and that's kind of what we're going to discuss today. So let me show you, like, I'll show you an animation unless there are any questions so far. Makes sense up to now. So yeah, like the best way to think about these things is some sort of like, you know, you are applying like a filter to what you see, and then it changes like the way the image looks. So, and this correction factor is called the Jacobian in general, so I'll give you the name in a second. Let me just show you what this looks like. Okay, so here, let me see if I can zoom it. Oh, actually, it's better to have like the description of what's going on. So, on the right hand side, you see like a regular region on the XY plane, right? So like the region has this particular shape. So that is, think about it like what you would actually see with your eyes. That's one way to think about it. So now you're making a change of variables, which is analogous to like saying r equals r cosine of, sorry, which is analogous to saying x equals r cosine of theta and y equals r sine of theta. It's just that instead of like giving the change of variables in terms of r and theta, you just give it in terms of new variables, which you just call u and v. In general, like you don't try to get like into the business of giving like a specific name to every single change of variable. So like typically like the new variables are yours called u and v, and that's kind of how we will treat them for today's class. So, but think about this as some sort of like analog of polar coordinates, right? It's just like there's no specific name for it because it's not that used. Like, it's very like specific to this particular problem. It's not as useful as polar coordinates. Okay, so the point is that these change of variables happens to have the property that this entire region, which is kind of like a triangular in a sense, but it's not quite a triangle, right? Because this is a little bit curved. This entire region, if you were to plot it with respect to the new variables u and v, becomes like a huge square or a huge rectangle. So like a deformation like changes like this pseudo triangle into like more of a square. Okay, and so the one of the effects of that, because of the distortion, right, is that, for example, this thing, which is not like it's like again like a let's call it curved rectangle for lack of a better word. So like this curved rectangle becomes an actual rectangle here, or like an actual square, but like like here, like they are like literal squares. So it's easy to find the area because like the distance here is 0.2. So 0.2 times 0.2 is 0.04, right? But like the real area, the real area on the XY plane was like, it was not 0.04, it was 0.05, blah, blah, blah. So these two areas do not match, right? And then you need to multiply by something that will compensate for the distortion and make these numbers coincide. So the point is here is like if you do 0.04 times this thing called the Jacobian, which will be the correction factor, you will recover the correct area. What's interesting here is that, for example, if you move, if you move to this square, like it corresponds to this larger curved rectangle on this side. So it's the blue square still has like the same area, 0.04, right? But now like this area has increased, so the correction factor needs to increase as well. So like now the Jacobian would increase in size. And like if, for example, if you move somewhere closer to the origin, this one nice. If you move closer to the origin, now this square is like one that matches to this curved square. And now you like, this is smaller, and that way like the Jacobian has to adjust itself so that like it continues to be true that roughly this thing times the Jacobian gives you the area on the other side. So my point is that, when you have like the original picture and you plot it in the new with new axes corresponding to the new variables, it gets distorted. And so to kind of preserve the correct values for the areas on this side, you do have to multiply the areas that you get here for by something, which can change. So it will be like a function in general. And that is what we'll call the Jacobian. Okay. So making sense, kind of like an idea. So it's just areas get distorted, and so you need to compensate for the distortion, right? So it's not that different from how lenses or other like optical like apparatus work, like in actual real world. So let me give you like an idea of like where how the formula, like where the formula comes from. And again, I won't try to get into too many details because then it would take too much, but at least you'll get some sense of what's going on. So let me see. Here's my eraser. Oh yeah, I'll give you like the formula for the Jacobian, and then we'll do some examples with it. So the idea is that you have like a change of variables where are going to think of X and Y being given in terms of two new variables, U and V. Um, so here we want to think in terms of two new variables, U, V. So, for example, like the one that I just showed you on the animation. So, for example, x equals u squared minus v squared, y equals 2uv, or here's like another example, x equals u plus v and y equals u minus v. This is another one. Here's another example, u or v cosine of u and y equals v sine of u, right? So those are, in general, like you will be given the change of variables, so there's not something you have to worry about coming up with. The last one hopefully looks pretty similar, like familiar, right? It is essentially polar coordinates if you think of V as being R and U as being theta. So this is actually polar if you take, if you call R equals V and U equals theta, right? So it's secretly like, so polar, my point is that it's contained into the stuff that we're doing right now. Is just that polar is so useful that it kind of deserves its own lecture or whatever, but you know, it is a special case of what we're discussing now. Is that making sense? So, so you have like all those changes of variables, and my point is that if you know, if you have like just to kind of draw something similar to what we saw in the animation. I'll put it, in the same way as in it showed up there. So in the animation, we had like some sort of like square rectangle here. Let's think about it more like as a rectangle. I had like a rectangle on the UV world or plane, And that corresponded to like a deformed, like, or like a curve, some sort of like curved square on the real world, right? So let's just try to do this, something like this. Okay. Um, so that is what you get there. Now, so what's happening here? Again, like in calculus, you have to think of everything as being really, really small. Uh, so for example, let's say that this is u, this is v, right? This is like the value u comma v, or this vertex, or this corner of the rectangle is the point u comma v. And then from this point to this point, how much you're going to move, like an amount delta u. So let's say here you're moving delta u. So you get to the point u plus delta u and then v. And in fact, like, let me start using different color because that would be useful in a moment. So because I do want to pay attention to the four. Okay, and then there's another, like, from here to here, now you are increasing in height, right? Which is like the variable v. So let's say that the increase is delta v. Now this is the point u comma v plus delta v. And for the last point, well, you move delta u and then you move delta v. So this will be u plus delta u v plus delta. Okay. Is that making sense? So this, like, again, like as a rectangle, right? Like like the area, like I'll put it in quotes, right? Because the area would be, as a rectangle would just be like delta u delta v. Or let's just say delta v delta u. Because it's still like, again, like if you just forget like about where this comes from, you just see a rectangle and you would say, okay, this area is base times height. Okay. So far, so good questions. So now what I'm saying is that each of these vertices corresponds to one of the corners that you see on the right hand side. So for, just to kind of make our life easier, like let's say this point corresponds to this point, okay? I'll call like this point x comma y, okay? And for example, this point corresponds to this point. Call this x. Okay, now this is different, like this in principle could have different values of x and y, right? So like really you are moving like an amount delta x and delta y, both cases. Okay, so okay, so like these 4 points P, Q, R, S, they are they correspond to the 4 points that I'm drawing here. P, Q, R, S. And I could still, I could still give valid like entries to the other 2 points, but that's a little bit more than what I need for now. Okay. Um, So what's happening here is that you do want like an area, like you want like a formula for the area of this piece, right? So what is the area here of this region? Okay, and this is where the stuff from the first exam comes in, because the idea is that this is not a rectangle, like not, definitely not a rectangle. So the best, like if you want to kind of find like an approximate value for this area, what you can do, let me see which colors I want to use. Okay, I have these remaining colors. What you can do is approximate these by the area of a parallelogram. So if you remember, like this vector goes from P to Q, right? So that's what we would call the vector PQ. So back to the first exam, and this goes from P to R. So this is what we would call the vector PR, right? So if you complete the parallelogram, you're getting something that looks like this. Right, so I'm just saying like, I'm going to approximate, and again, this is gonna be a bit messy, so let me just try to color it a little bit without making like a huge mess on the picture. So I'm just saying like, okay, that area of the parallelogram is obviously not in a quite 100% the same as the area of the actual region, but you know, the idea is that if you think about making delta U and delta V very small, then the difference between the area of the parallelogram and the area of the actual region will go to zero. So that's kind of like how the argument is supposed to work. Now, so like what I'm trying to say is that I'm trying to approximate it. So just approximate it by area of parallelogram with size PQ and PR. So so what was the formula for the area of a parallelogram in terms of the two vectors? Yeah. Correct, yeah, good. So the area has to be close to the magnitude of PQ cross PR, perfect. So let's just like, let me show you, like, then like what you have to do is like an approximation of an approximation. Then you have to approximate like the vector PQ. So let's just do that for PQ because like the other one is pretty similar. So I'll just show you like the main idea for what the vector PQ is. So let's see, what is PQ? Well, PQ, if you remember, the way to find it is like Q minus P in terms of coordinates. So the coordinates for Q are x plus delta x, y plus delta y, minus the coordinates for P, the coordinates for P are x comma y, right? So that, I mean, the x and y cancel out, right? When you subtract the entries, so you just get delta x comma delta y, right? So this is what the vector PQ is. Is that making sense? And then I'll go do a trick, because how does this originate? This is like the difference from this point to this point when you change here from this point to this point, right? So when we went from the yellow to the orange point here, what we changed was delta U. Okay, that's the only change that we did. We preserved the value for V. So this changing points is coming from the corresponding change in delta U. So kind of like the calculus trick, like it's a little bit of a cheating, but like, you can like just to emphasize this, like I'll put it like I'll divide and multiply both sides, and I'll divide and multiply by delta U. Okay, that is completely harmless because that's fine, like But now this, like what is delta x over delta u? That's like a ratio, like a rate of change kind of like of x when you change u. So it's like a partial, it's basically like the partial derivative of x with respect to u. So this, like the approximation is that this is like approximated by the derivative of x with respect to u times delta u, comma, the derivative of y with respect to u times delta u. Okay, so what delta u is the same, well, it's like kind of making sense. So like what I'm saying is that this vector roughly is like it's basically determined by these partial derivatives with respect to u. And let me write this down. So PQ, I'm just saying like I'll take it to be like the derivative of x with respect to u times delta u times the derivative of y with respect to u times delta u. And kind of because of the like it would be like similar idea like for the vector PR. For PR, that happened when that came from changing delta V. So like there's like a similar argument that PR would be roughly the vector equal to the derivative of x with respect to V times delta V, the derivative of y with respect to V times delta V. That's a good.
How did you make that argument with delta V and for P?
Oh, for PR? So let's say when on this side, when you move from P to R, right? What did you change? You change V, right? And so the change from P to R on this side is also because you change V on that end. And so that's why it becomes like the derivative with respect to V instead. Okay, and the last thing, and now before giving you like the final formula, it's like kind of cute, like is what's the, I mean, basically you have the vector, so you can take their cross product, right? So if you remember like the way to take a cross product, if you do the determinant formula, you put ijk. This is nice because like the third entry is 0, right? Like they're like on the plane, so like the last entries are 0 in both cases. So like you put the term partial of x with respect to u, delta u, partial of y with respect to u, delta u, and partial of x with respect to v, delta v, partial of y with respect to v, delta v. Okay, and maybe you remember when you did this cross product calculations, when there are zeros, like the cross product does simplify a lot. And so because there are zeros in the last two entries for both vectors, really in the cross product, the first two entries will be 0. So you get 0, 0, and then really like the only thing that you get is like these two minus these two, right? Like kind of like the determinant of these two by two matrix. So just to make it look at it a little bit nicer, because you see, like when you multiply them, you get delta U, delta V, and when you multiply this, you get delta U, delta V. So I'll just factor that one out. So it will look something like this. Okay. And so it's like the entries are 0, 0 times this thing. So the, like, the magnitude of this vector, right? Like, because it's Pythagoras theorem, but like the first two entries are 0 squared plus 0 squared. So you really don't see that. So when you take the square root of the square of this, you just get it in absolute value, right? So the area is just really approximated by the absolute value of this thing. So the absolute value of this quantity times delta V delta U. Okay. And what's nice about this, that's saying like the formula for the real area, for the true area, right, is a number or a quantity times the area in the like UV plane, right? Like, so this is like the area of the rectangle in the UV plane, right? Area of rectangle in the UV plane. So that it kind of gives us like what the animation was showing was what the animation was showing is that if you take the regular area of the rectangle on the UV plane and you multiply it by a quantity, you will recover like the true area, right? So this stuff is what I will call the Jacobian in a second. So this is kind of relating like the true area versus like the area on the UV plane. Is that making sense? So like if I'll do some examples after this, but in practice, what this means is that, you know, that is essentially what we were looking for because it's telling you, you know, how to find like the true area in terms like, you know, of the areas of the UV plane. And that is, this will be the term that goes into the double integral, you know, this will be the term that goes into the double integral when we do the change of variables. Or, so like the way, if we want to think about this more like properly in the Calc 1, Calc 3 version is that, what I'm saying is that dy dx, because that's kind of like a very small piece of area in the real world, right? What this is saying is that dy dx is basically this thing times dvdu. So that is like when we do the changes of variables, like the formula that we will use for conversions, like the double integrals. So let me write all of this down like a bit more precisely. And like you should compare this, like, sorry, to make it more clear, compare this with the formula in polar that we had with dy dx equals r dr d theta, right? Right, because that's what essentially we were doing in polar, where we were switching from Cartesian to polar. We were literally changing the y dx into r dr d theta. So this is like the analog. It's just that all of this replaces what was r in polar. Yeah. Okay. So let me kind of write down like the formula, and then I'll just do some examples to show you how this all looks. So what the change of variables says is that and like this can be written in terms of a matrix, which is a bit nicer. So I'll write it that way. So put this here. If you write x and y in terms of UP, if you write x, y in terms of then dx, I mean dy dx, which is the same as the y, dx dy, I'll just emphasize that. That becomes the absolute value of the determinant of J. So like where J is called the Jacobian matrix, where J is the Jacobian matrix. Yeah, and that is the only formula actually for today's class. But everything, every problem is really a consequence of this formula. Oh, let me put it.
How would you go about taking the absolute value of the determinant if it's like sometimes negative, sometimes positive?
Oh, okay, so if that happens, when you do like the double integral, like say you would leave it in absolute value and then you break the double integral so that you can, get rid of the absolute value. So for example, I mean, in practice for the problems we'll work with, usually like it will be either always positive or always negative, but say if if the, I'll do some examples of Jacobians in a second, and then you'll see what I mean, but like, yeah, if we gave you something where like you don't know whether it's sometimes positive or sometimes negative, you would split the double integral so that you can get rid of the absolute value, if that makes sense. But no, that's a good question. I'll show you in a bit, like a few examples about that. Uh, Okay, let me do some examples of Jacobians and then I'll do some problems so that you see how this all works. Okay, so let's do it first for polar to show you that it really recovers the formula from polar coordinates. I'll do like well, I'll do just two examples of finding these Jacobians and then I'll do like actual problems in the way that you will be given those problems. So let's say the change of variables is like x equals v cosine of u and y equals v sine of u. Okay, again, secretly, I'm thinking here of r being v and theta being u. So here r is v and theta is u if you want to compare this with polar, right? If you want to compare it with polar, if comparing with polar. So what is the Jacobian matrix in this case? Is this thing, which is the derivative of x with respect to u, the derivative of y with respect to u, the derivative of x with respect to v, and the derivative of y with respect to v. So it's a 2 by 2 matrix. What's the derivative of x with respect to u? That's minus v sine of u. What's the derivative of y with respect to u? That's v cosine of u. What's the derivative of x with respect to v? That's cosine of u. And what's the derivative of, y with respect to v? That is sine of u. Is that okay? Is that making sense? Like how I found those partial derivatives so far so good. And like I'll write it in the r theta versions psychologically. It makes more sense. So like v is like r, right? V is like r. So this is like minus r sine of theta because u is theta, right? And then this is r cosine of theta, right? And then this one is cosine of theta, and then this one is sine of theta. So it kind of is easier to process it if you write it this way than in terms of u and v. Now, what is the determinant of this matrix? Okay, what is the determinant of J? Well, remember, it's this one times this one that gives you minus r sine square of theta. And then there's a minus that comes from the formula of the determinant, right? So minus this one times this one. So you get negative r sine square of theta minus r cosine square of theta. You can factorize a negative r, right? So you get sine squared plus cosine squared. Okay, this gives you one, right? Because sine squared plus cosine squared is one. So that means that the the determinant of the Jacobian matrix is minus r in this case, right? So the change of variables formula, right? What the change of variable formula says is that dy dx is the absolute value. Let me put it, I'll emphasize it with a different color. The absolute value of the determinant of j times dr d theta. But when you say the absolute value of this, it's like the absolute value of negative r. Okay. And so that's just r dr d theta, right? Like that's essentially because r is always a negative in polar. Oops, let me. Okay. Is that making sense? So I'm just saying like, in the case of polar coordinates, like the formula does give you back the formula that I gave you last time, but the way we kind of found that in this way, in this case, is a lot more like algebraic because if like in the case of polar last time, we had to pay a bit more attention to the, like the pictures and everything, but once you have this formula for changing variables, like, and then finding the Jacobians is pretty straightforward, okay? Everything sense. I'll do another example with Jacobians, and then I'll do more examples for actual double integrals. But at least I should find another Jacobian. So let's see. Here's another example. Oops, I don't want to erase this. Here's example 2. Let's say that x is the one that was on the GeoGebra animation. So u squared minus v squared. And y is 2uv. Okay, what would be in this case the Jacobian matrix? So it is derivative of x with respect to u, derivative of y with respect to u, derivative of x with respect to v, and derivative of y with respect to v. Okay. So what is derivative of x with respect to u? That's 2u. Derivative of y with respect to u, that's 2v, right? Derivative of x with respect to v is negative 2v, right? And derivative of y with respect to v, that's 2u, right? Am I making sense? And so the determinant in this case of this matrix would be what? Is 4u squared minus minus becomes a plus, so you get 4b squared, right? Okay, that's just 4 times u squared plus v squared. And what the change of variable says is that dy dx, which is the same as the x dy, right? According to the change of variables formula, that is the absolute value of the determinant times dv du. It's just that in this case, well, this is clearly already non-negative to begin with, right? Because it's like a sum of squares. So here, like, there's no need to put, like, I'll put it with absolute value first, but I'll remove them right away because there's nothing to worry about in this case. And so you get 4u squared plus v squared times dv. Okay, so in general, you will be given the change of variables. So let's do like an actual problem for like computing like an actual double integral so that you see how this works. Okay. But these problems, think about them as kind of like generalizations of polar coordinates. So that's kind of like the type that it has. Okay. I'll just erase on the left side if that's okay, because like we don't have too much space. So So here's an, I'll do. I think 2 examples should be enough. I think we have enough time for 2 examples. So let's just do the integral. Where R is a region in the first quadrant. Is a region in the first quadrant. Determined by the lines. By, let's see, y equals x, y equals 4x. Y equals 4 over x, sorry, y equals 1 over x, and then y equals 4 over x. Okay, let's do that. And sorry, I forgot. The change of variable that you use is to use x equals root of u over v and y equals root of u times v. So again, like the change of variables is provided always for you, so. That is what is going to be in this case. Okay. Here's a recommendation for doing this problem. The Jacobian is always entirely algebraic, like finding the partial derivatives and taking a determinant. So you can always do that first at the beginning of the problem, but to have it around when it's necessary. So let's try to find the Jacobian. And then, as always, like we have to think about what are the bounds. Maybe yeah, I'll find the Jacobian and then I'll draw the region and then we'll determine the bounds from there. But if you think about the Jacobian, for taking we need to take derivatives. It is easier to write like these formulas in using like the exponent notation. So let's write x as u to the 1/2, v to the -1/2, and y as u to the 1/2, v to the 1/2. That actually makes it easier to think about how to find these things. So J, the matrix is derivative of x with respect to u, derivative of y with respect to u, derivative of x with respect to v, and derivative of y with respect to v. Okay, and then let's take the partial derivatives here. There's just a bunch of 1/2s in this formula. So you get 1/2 of u to the -1/2, because remember the exponent drops by 1, v to the -1/2. Then with y, it is 1/2 u to the -1/2, v to the 1/2. Okay, so that is the first row of the matrix. And then for the second row, when you do it with respect to v, you get -1/2 u to the 1/2, v to the -3/2. That's the difference here. And then when you do it for y with respect to v, you get 1/2 u to the 1/2, v to the -1/2. Okay. It does simplify a lot, so it's not as bad as it looks right now. Is that making sense? Any questions up to now? Okay, so what do you get? What do you end up getting here? Like when you take the determinant. Okay, when you multiply the first diagonal elements, like the u to the negative 1/2 cancels this u to the 1/2, and this becomes v to the negative 1. So you get a quarter of v to the negative 1. And then minus minus becomes plus, and it's kind of like the same idea. So you get plus a quarter of v to the negative 1/2. So the Jacobian is just 1/2v. So it's not as bad as it seems, right? Like from the matrix presentation, like it's a lot more simple. Okay, so that like let me put it here underneath the change of variables because it's kind of nice to have it somewhere. So I'm just saying like in terms of point strategy, these are easy points in the sense that it's just finding the partial derivatives, taking the determinant, like it's completely algebraic. You just have to be like patient when finding everything, but that would be the determinant of the Jacobian. Okay. Now let's draw the region on the XY plane. So here, like the interesting thing about this problem is that to find the like you can draw the regions on the XY plane that it's not as useful as drawing it on the UV plane. That's the whole point of doing the change of variables. But you'll see that on the UV plane, like everything becomes a lot more simple. So let me start by doing the lines. So the first is going to be y equals x, which is something like this. Then it will be y equals 4x. Everything is on the first quadrant. That's why I'm only drawing like the stuff on the first quadrant. Y equals 4x. Then y equals 1/x. Looks something like this. And the other one, y equals 4/x. Looks like this. Okay, so it's kind of like an interesting picture. The region corresponds to that. And so, like, even just from the picture, even like, it's not super precise, but you can kind of tell that if you try to do it in Cartesian coordinates, it's a bit of a mess because you will have to break the region regardless of, how you set it up. Either order the y dx or the x dy do require at least two double integrals, and then after that there's I mean, yeah, like the fact that there are two double integrals is not super nice. So now what I want to do is check or find how each of these curves looks on the UV plane. So how can I do that? So let's start with the first one, y equals 1/x. That's the same as saying y times x times y equals 1, right? But what is x? Like I can put it as root of u/v. And what is y? Y is root of uv, right? So now I'm rewriting this in terms of u and v, right? And what happens here, like the v's cancel out, and the square roots like just give you u. So this looks like u equals 1, like the curve, the line becomes u equals 1 on the UV plane. And u equals 1 is somewhere in here. Is that making sense? Kind of how I found it. So like basically what I did was rewrite the equation. Like it's kind of like the same where we were doing when we're going from Cartesian to polar, right? Like you would just rewrite the equations in terms of r and theta. I'm rewriting the equations now in terms of u and v. Okay. So that is the first one. And for the other sorry, this is like this wasn't for the line, this was for the hyperbola, right? Like, because it was the orange one. For the other hyperbola, which is y equals 4/x, it's kind of the same, but there's like a 4, like, so you get xy equals 4, and you do the same, so you root of uv equals 4, so you get here u equals 4. So this other hyperbola becomes u equals 4. So it looks like this, right? And let's do the same for the other two. So what can you say about y equals x? Y equals x is the same as saying the root of uv is the same as root of u over v. And again, because of the same idea, like the roots of u cancel, and then you multiply by root of v, so you just get that v equals 1. Okay. And for the last one, which is y equals 4x, what happens with y equals 4x? You get root of uv equals root of u over v. And because of the same, like, you get v, but now v equals 4, and v equals 4 looks like this. So this region R on the UV plane gets transformed into this thing. Okay, so now the integration is very easy. It's taking place on a square, right? Basically. So the bounds will be very easy. You would go, U is going to go from 1 to 4, and V is going to go from 1 to 4. Is that making sense? Any questions about this? And like the idea is, well, I still haven't finished it because we have to transform the integral. Every single problem about UV changes of variables is exactly the same. You're given a change of variables, find the Jacobian first, then change each equation that determines the region into U and V, and that is what determines the bounds, like, that is what determines the bounds for the double integral in terms of U and V. So let's try to do the double integral. Okay, so the double integral was an integral for x squared plus y squared. So what is x squared plus y squared? Let's think about it. X squared becomes u squared over v squared, right? And then y squared becomes uv, right? I'm sorry, when you square it, like, you just get u over v, right? So like the square roots go away. So you get, and then y squared just uv. So that is what this gets changed into. And then the y dx, right? I'll just put like this gets changed into the determinant of the Jacobian in absolute value times dv du. Okay. So that's what the change of variable says. And then the bounds, we already have them because we already have the region. So v goes from 1 to 4, and u also goes from 1 to 4. Does that make sense? And what is the Jacobian is 1 over 2v. I mean, like, here v is always positive, right? So like, you don't have to worry about the absolute value. So I'll just replace this with 1 over 2v. One over 2v dv. And so, okay, like, I will just give you what the answer, like, again, for many of these problems, like, usually once you get to this point, like, the integral would be easy to do. This one is not particularly super easy. I mean, it's not bad, but it does take a while to you do it. So I'll just set it up and tell you what the answer is. So, you know, like you can just write this as u over 2v squared plus u over 2 divided du. So again, like in practice, like, you know, for practical purposes, like the integrals that you would always do are more simple than that because it is a bit long, because it's a sum, so you have to do two integrals really. But that's okay, let's say. The important thing is that, well, once you do that, I think you get like 225 over 16 or something like that. But is the you know, the main idea for this integration. Like this is what that integral would give you. Let me think something. So again, like in practice, like again, like maybe like realistically, like everything ends up being like u, and then you integrate u divided u or something easier than this. So don't worry too much if the integrals looks a bit too complicated. The important thing is that the effect on the bounds, if you look at it, is very drastic because it changed from being like this region where like there's no really good way of doing it except like breaking it into to double integrals into something where the bounds become completely constant. So it's kind of like just to understand that that's like the philosophically the point of changing variables. Then sometimes like problems that are too long with x and y become really relatively easy in terms of new variables. Okay, so there is another example in the video recording that I usually send you on each announcement. So if you want, like once I send you like the announcement tonight, if you want to watch that extra example, you can see it on the video. It's on the PDF notes. But let's finish here because we wouldn't have enough time to, we only have 10 minutes left. So next time, what I'll do is on Monday, I'll start doing triple integrals and I'll send you the announcement later this week about the extra office hours for next week for the exam. Okay, but yeah, I think let's wrap it up here.